Hello, dear friend, and welcome to the Dreamy Lab channel. Tonight, we're drifting into a realm where the familiar laws of nature begin to blur. A place smaller than atoms, quieter than silence, and stranger than imagination. This is the quantum world, where reality bends, certainty dissolves, and the limits of science are gently tested. This isn't just a story of discovery, it's an invitation to wonder. Imagine the world around you beginning to shrink. Not quickly, but softly, as though everything is being viewed through a lens of stillness. Smaller than dust, smaller than cells, smaller than anything even our most powerful microscopes can reveal. At this scale, the solid objects you once trusted, the chair, the air, even your own skin, are revealed to be almost entirely empty space. What once felt firm and familiar is now a delicate arrangement of invisible patterns. For a long time, atoms were believed to be the smallest possible pieces of existence, the final bricks of reality. Tiny, indivisible, and complete. But as science peered deeper, something astonishing was found. Atoms were not the end, but the beginning of a deeper mystery. Inside them lives the quantum world, where particles behave in ways that defy logic and expectation. In this hidden realm, certainty fades into softness. Particles do not sit in one place, nor do they move with predictable speed. Instead, they drift as waves of probability, existing as possibilities rather than fixed things. It is a universe guided not by solidity, but by rhythm and chance, far removed from the world of touch, weight, and form. How can something be both particle and wave? How can it exist in many places at once, or nowhere in particular at all? These questions are not flaws in our understanding, but signs that nature itself is deeper and gentler than we once believed. And so, with quiet curiosity, we begin our journey into the atom, its structure, its discovery, and the steps that open the door to quantum mechanics. But before science unveiled these truths, the idea of the atom began not in laboratories, but in the imagination of ancient thinkers. Thousands of years ago, in Greece, philosophers wondered if the world could be broken down into tiny, uncuttable pieces. They named these pieces atomos, meaning indivisible. To them, atoms were eternal, solid, and unchanging, forming the foundations of everything we see. This early vision wasn't built on experiments, but on pure thought. It was an attempt to bring order to the ever-changing world, to find something constant beneath all transformation. Their atoms were simple, still, and silent, nothing like the restless and mysterious particles revealed by modern physics. As centuries passed, science gained new tools, sharper questions, and clearer evidence. Researchers discovered that atoms were not solid marbles at all, but vast spaces containing even smaller parts. Electrons drift not in neat orbits, but in soft clouds of probability around dense centers made of protons and neutrons. And these tiny pieces do not behave like miniature stones. They shimmer between states, sometimes acting like particles, sometimes like waves, guided by invisible mathematics and subtle forces. The journey from ancient philosophy to quantum science is one of humanity's greatest transformations in understanding. It reveals that reality is not always what it seems, that beneath the surface of the ordinary lies a universe shaped by uncertainty, beauty, and possibility. The atom, once imagined as final and simple, is now known as a doorway, leading into a realm where the rules bend, dualities coexist, and existence itself becomes a dance of potential. In that quiet space beneath everything we see, the cosmos whispers its deepest secrets, waiting patiently for us to listen. In the early 19th century, the story of the atom entered a new era through the work of John Dalton, a British scientist who transformed an ancient idea into a practical scientific model. Dalton proposed that everything in the world is made of tiny, indivisible particles called atoms, small, solid spheres that combine in fixed ways to create different substances. His theory marked a turning point in chemistry, offering a clear explanation for why matter behaves the way it does. According to Dalton, atoms of a single element were identical in mass and properties, and entirely different from atoms of other elements. He imagined them as miniature, solid balls, each with its own weight and identity. To him, Chemical reactions were not mysterious changes, but simple rearrangements, atoms coming together or separating, without being destroyed or altered internally. Though simple, Dalton's vision was powerful. His model helped explain why compounds form in fixed ratios, like how water is always 2 parts hydrogen and 1 part oxygen. His atomic theory turned chemistry into a science of particles rather than guesses and alchemy. It laid the groundwork for understanding matter as something built from smaller, measurable pieces, not magical transformations. But even groundbreaking ideas have limits. Dalton believed atoms were indivisible, yet the universe had more to reveal. As the century progressed and scientific tools improved, cracks began to appear in the solid sphere model. Atoms were not the final layer of reality, they contained even smaller parts. Still, Dalton's work was a bridge. It connected ancient philosophical guesses with experimental science, turning imagination into investigation. His model inspired new generations to look deeper, leading science from the idea of unbreakable spheres into the strange landscape of subatomic particles and quantum behavior. The evolution from simplicity to complexity mirrors the atom's own unfolding mystery, shifting from solid blocks to dynamic systems filled with motion and uncertainty. By the end of the 19th century, new discoveries began to challenge Dalton's picture of the atom. The idea of a solid, indivisible sphere started to fade when an English physicist named J.J. Thomson conducted experiments that revealed something astonishing. Atoms were not the smallest things in existence. In 1897, while studying glowing beams called cathode rays inside vacuum tubes, Thomson made a discovery that changed science forever. He found that these rays were made of tiny, negatively charged particles far smaller than any atom. He called them electrons. For the first time, scientists had proof that atoms were not solid and indivisible. They had internal structure. This raised new puzzles. If atoms contained negative electrons, what held the positive charge? And how were these particles arranged? Thomson proposed the plum pudding model, a sphere of positive charge with electrons scattered inside it like raisins in a dessert. Although this model was later replaced, it was an important step in understanding the atom's true nature. Not long after, other subatomic particles were identified: protons, carrying positive charge, and neutrons, electrically neutral but adding mass. These discoveries revealed that atoms were not simple at all, but tiny systems with structure and balance, a kind of hidden universe made of smaller pieces. This growing knowledge transformed both chemistry and physics. Matter was no longer made of simple, solid spheres, but of complex, interacting particles. The atom became something alive with movement, balance, and energy. And this was only the beginning. These early breakthroughs opened the door to an even stranger world, the quantum realm, where particles behave in ways that defy classical logic. A world where certainty fades, positions blur, and reality reveals its hidden layers of mystery. From here, the journey into the quantum age begins. Around 1909, Ernest Rutherford and his team set out to investigate the hidden structure of the atom with a remarkably clever experiment. They aimed a beam of tiny, positively charged particles, called alpha particles, at an extremely thin sheet of gold foil. According to the plum pudding model of the time, these particles were expected to pass straight through with almost no disturbance, since the atom was believed to have its positive charge spread evenly across a diffuse cloud. But what they observed changed science forever. Most of the alpha particles did pass through with little to no deflection, just as expected. Yet a small number behaved in ways no one could explain. Some were sharply deflected to the side. A few even bounced backward, as if they had struck something incredibly dense and solid. This shocking result suggested a startling truth. The atom's positive charge was not spread out at all. It was concentrated in an incredibly small, dense region at the center. Rutherford proposed a new model to explain this. Nearly all of an atom's mass and all of its positive charge, he said, are held in a compact core, the nucleus. The electrons, instead of being embedded in a positive pudding, must orbit this central nucleus like planets around the sun, though on a scale far beyond imagination. This nuclear model overturned the old view and transformed our understanding of matter. It explained why most alpha particles sailed through untouched. The atom is mostly empty space. But it also raised new questions. If electrons orbit the nucleus, why don't they lose energy and collapse inward? Classical physics had no satisfying answer. Rutherford's gold foil experiment became a turning point, marking the birth of modern atomic physics. It revealed a hidden architecture within matter and paved the way for the quantum revolution, an era where probability replaced certainty and intuition no longer matched reality. This glimpse into the atom's heart encouraged science to keep looking deeper into the smallest building blocks of existence. Building on Rutherford's discovery of the nucleus, Niels Bohr introduced a bold new vision in 1913. He proposed that electrons do not orbit the nucleus randomly, but travel in specific, stable paths, or shells. These orbits were not continuous like planetary paths, but quantized, allowed only at certain energy levels. This was a revolutionary idea. Bohr suggested that electrons could remain in these fixed orbits without losing energy. They did not spiral into the nucleus as classical physics predicted. Instead, electrons could jump between these levels by absorbing or releasing precise packets of energy, called quanta. This insight explained a long-standing mystery: the distinct spectral lines seen when elements emit or absorb light. Each line came from an electron transitioning between specific energy levels. Bohr's model worked beautifully for hydrogen, the simplest atom, and gave scientists their first successful bridge between classical physics and the new quantum world. Yet the atomic realm was stranger than Bohr imagined. His planetary picture, though elegant, struggled to describe more complex atoms. Still, his work marked a crucial turning point. It hinted at a deeper truth. At the smallest scales, nature does not move smoothly and continuously, but in discrete steps governed by fundamental rules. Bohr's model opened the door wider to quantum mechanics. It invited us into a world where electrons do not orbit like planets, but exist as probabilities, waves, and possibilities, a world where reality is softer, stranger, and more subtle than the eyes can see. Niels Bohr's planetary model of the atom marked a bold leap in understanding. But as scientists ventured deeper into the atomic world, it became clear that the familiar laws of classical physics could not explain the strange, unpredictable behavior they observed at microscopic scales. The comfortable certainty of 19th century physics began to crack. One of the first major puzzles was the photoelectric effect. When light shines on certain metals, it knocks electrons loose. Classical wave theory predicted that brighter light would gradually increase an electron's energy. But experiments revealed something startling. Electrons were only released when the light reached a particular frequency, regardless of brightness. It was as though light arrived in tiny packets rather than continuous waves. In 1905, Albert Einstein explained this by proposing that light is made of discrete particles of energy called quanta or photons. His idea helped launch an entirely new way of thinking, quantum theory. Around the same time, Max Planck discovered that energy is not absorbed or emitted in smooth flows, but in fixed, measurable amounts. These ideas shattered the classical belief that energy changed continuously. Soon after, the mystery deepened. Scientists discovered the unsettling concept of wave-particle duality, the realization that particles like electrons could behave both as solid points and as waves. In 1924, Louis de Broglie suggested that all matter, not just light, might have wave-like properties. The claim sounded impossible until experiments proved him right. When electrons were fired through thin crystals, they formed interference patterns, the unmistakable signature of waves. This invisible duality destroyed the classical image of electrons as miniature billiard balls moving along fixed paths. Then came Werner Heisenberg, who delivered another blow to certainty. His uncertainty principle revealed that there are strict limits to how precisely we can know certain pairs of properties, like an electron's position and momentum. This wasn't due to imperfect tools. It was a built-in feature of nature. Taken together, these discoveries gave rise to quantum mechanics, a revolutionary framework based not on fixed outcomes, but on probabilities, wave functions, and intrinsic uncertainty. The classical world of predictability faded, replaced by a realm where observation itself changes reality. This shift was unsettling, even to the scientists who created it. Yet it opened a doorway into the hidden structure of existence, revealing a universe far stranger and far more elegant than anyone had imagined. At the heart of the quantum world lies one of its most astonishing truths. Things like electrons and photons don't belong to a single category. They are not simply particles or waves. They can behave as both, depending on the situation. Light offered the first clues. For centuries, it was treated as a wave, explaining diffraction and interference. But the photoelectric effect proved that light can also behave like a stream of particles, with each photon carrying a precise amount of energy. De Broglie then extended this paradox to matter itself. He suggested that electrons, tiny components of atoms, also possess wavelengths. Soon after, experiments confirmed it. When electrons were passed through crystals or slits, they produced the same wave-like interference patterns seen with light. This duality defies everyday intuition. How can something act like a particle one moment and a wave the next? The answer lies in the wave function, a mathematical description that gives the probability of where a particle might be, rather than a definite location. Wave-particle duality is not a minor curiosity. It has become the foundation of modern technology. Electron microscopes, semiconductors, lasers, and quantum computers all rely on this strange dual nature. As the story continues, this concept will guide us through the deeper mysteries of atomic structure and the astonishing rules that govern the smallest building blocks of existence. One of the most mesmerizing demonstrations of wave-particle duality is the legendary double-slit experiment, a puzzle that has fascinated physicists for more than a century. In its simplest form, a beam of light, or even particles like electrons, is aimed at a barrier with two very narrow, closely spaced slits. Behind it sits a screen that records where each particle or photon lands. If particles behaved like tiny bullets, we would expect to see two bright clusters on the screen, each one lining up with a slit. But that isn't what happens. Instead, a pattern of alternating bright and dark bands appears, an interference pattern, just like overlapping ripples on the surface of water. Bright bands form where the waves reinforce each other. Dark bands appear where they cancel out. This alone is astonishing, but the real mystery unfolds when the experiment is slowed down. Physicists send electrons, or photons one at a time, separated by seconds. Each one hits the screen as a single dot, clearly acting like a localized particle. But over time, dot by dot, they still build the same interference pattern, as if each particle somehow passed through both slits at once and interfered with itself. It's as though nature is quietly whispering, "I am not what you think I am." Then comes the twist. When detectors are placed at the slits to observe which slit the particle passes through, the interference vanishes. The elegant wave pattern collapses. The screen now shows two distinct clusters, exactly as if the particles simply chose one slit or the other. Nothing physical was changed, only the act of measurement was added. Yet the outcome transformed completely. This single result reshaped our understanding of reality. It implies that at the quantum level, particles do not follow definite paths. They exist as probabilities spread out in space, described by a wave function, until something measures or observes them. In that instant, the wave function collapses and one possibility becomes real. The double-slit experiment didn't just challenge classical physics. It overturned its foundations, revealing a universe woven from mystery, not certainty. Another pillar of quantum mechanics further deepens this shift: Heisenberg's uncertainty principle. At the quantum scale, reality is not crisp and defined. The more precisely you try to measure a particle's position, the less precisely you can know its momentum, and vice versa. This isn't due to flawed tools or human error. It is a built-in feature of nature. Imagine trying to pin down the exact location of an electron. The act of measurement itself disturbs it, making its momentum unknown. If you measure the momentum with perfect accuracy, its position becomes uncertain. The universe will not allow both values to be exact at the same time. This stands in sharp contrast to classical physics, where every object has a definite position and speed, whether or not we're observing it. In the quantum world, exactness dissolves into probability. The foundations of reality begin to look more like a cloud of possibilities than a collection of solid objects. Yet this uncertainty is not a flaw, it's essential. It helps explain why atoms are stable, why electrons don't spiral into nuclei, and why matter in our universe doesn't collapse. The uncertainty principle quietly shapes every bond, every interaction, every material that exists. It teaches us that nature is not a mechanical clock, but a dance of potential, always shifting, always unresolved until the moment of observation. Together, the double-slit experiment and the uncertainty principle invite us into a universe where certainty is limited, observation is powerful, and reality itself seems to wait in a state of possibility until we look. One of the most important tools for understanding the quantum world is Schrödinger's wave equation, developed by Erwin Schrödinger in the 1920s. Instead of picturing electrons as tiny billiard balls traveling along fixed paths, Schrödinger treated them as waves that spread out, overlap, and interfere, creating complex patterns of probability. These probabilities aren't just abstract numbers. They form what we call probability clouds or orbitals, regions around an atom's nucleus where an electron is most likely to be found. Unlike the neat, circular orbits imagined in early atomic models, these clouds are fuzzy, fluid, and ever-shifting, reflecting the uncertainty and dynamism of the quantum world. In quantum mechanics, it's no longer accurate to say the electron is here. Instead, we say the electron has this likelihood of being here. Schrödinger's wave equation allows scientists to calculate those likelihoods, revealing the intricate and often beautiful shapes that electrons inhabit. This approach radically transformed our understanding of matter. Atoms are not tiny solar systems, but probabilistic systems, where electrons blur through space in wave-like patterns described by mathematics. Schrödinger's equation became the bridge between unseen quantum behavior and measurable physical properties, making it a cornerstone of modern physics and chemistry. By accepting electrons as probability clouds rather than fixed points, we step into a universe where certainty gives way to possibility, a quiet dance of existence that defies everyday intuition yet builds everything we see. In quantum mechanics, the concept of a quantum state is essential. It contains everything that can be known about a particle or system at a given moment. But unlike classical physics, where an object has a definite position, speed, or energy, a quantum state allows for something far more mysterious: superposition. Superposition means a particle can exist in multiple states at the same time. An electron might be in different locations or hold different energies simultaneously, not one or the other, but both blended together in a single quantum state. Only when we measure the particle does this blend collapse into one definite outcome. This idea challenges everything our everyday experience tells us. We're used to objects being in one place or having one value. But at the quantum scale, reality holds its options open, multiple possibilities coexisting until observation tips the balance. Superposition isn't just a curiosity. It explains interference patterns and forms the foundation of quantum computing, where bits can represent both 0 and 1 at the same time. Embracing superposition invites us to see the quantum world not as fixed, but as a realm of soft possibilities delicately balanced until observed. Quantum entanglement is one of the most astonishing and puzzling features of the quantum world. When two particles become entangled, their properties become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. Albert Einstein once called this spooky action at a distance because it appears to defy the rule that nothing can travel faster than light. Think of two entangled particles as twins sharing an invisible secret. If you measure one twin's property, its spin, for example, you instantly know the other's, even if that twin is on the opposite side of the universe. This connection ignores distance, challenges classical ideas of space and time, and suggests a deep, underlying unity in nature. Extensive experiments have confirmed that entanglement is real, not a mathematical trick. And it's not just mysterious, it's useful. Entanglement forms the backbone of quantum computing, quantum encryption, and ultra-secure communication technologies, where information is processed and shared in ways impossible in the classical world. Entanglement reminds us that the quantum realm plays by different rules, a realm where separation is an illusion and particles can remain connected across the vastness of space in perfect, instantaneous harmony. The discoveries of quantum physics did more than add new chapters to science. They rewrote the foundation of how we understand reality. Classical physics, built on Newton's laws and the belief that particles moved along fixed, predictable paths, suddenly appeared incomplete. Quantum mechanics introduced uncertainty, probability, and duality, revealing that at the smallest scales, nature behaves in ways that defy everyday logic. Particles are not tiny billiard balls, but waves of possibility, and the act of measuring them can change the outcome entirely. This new view challenged the long-held belief that the universe functions like a perfectly predictable machine. Instead, quantum physics uncovered a reality where chance and probability play an essential role. Classical physics still governs our daily world, but beneath it lies a subtle probabilistic realm, a universe built on possibilities rather than certainties. This quantum revolution reshaped not just physics, but philosophy and technology, paving the way for breakthroughs like semiconductors, lasers, MRI machines, and quantum computing. Understanding how these ideas transform science helps us appreciate the quiet balance between order and uncertainty that holds the universe together. Beneath atoms, an even deeper realm unfolds, one composed of elementary particles, the most fundamental units of matter and energy. These particles are not made of anything smaller. They represent the base layer of physical reality as far as science has reached. Physicists classify these particles into two main groups: fermions, which make up matter, and bosons, which carry forces. Fermions include quarks and leptons. Quarks are especially vital because they combine in groups of 3 to form protons and neutrons, the particles that cluster in atomic nuclei. Without quarks, atoms could not exist. Leptons include electrons, the negatively charged particles that surround the nucleus and define atomic structure. Another type of lepton is the neutrino, an almost massless particle that passes through the Earth and through you by the trillions every second, barely interacting with anything. Each fundamental particle appears in different types, or flavors, with unique masses, charges, and behaviors. These differences determine how particles connect, combine, or transform, ultimately shaping everything from stardust to living cells. Opposite the fermions are the bosons, which act as force carriers, invisible messengers that allow particles to interact. Photons carry the electromagnetic force, making electricity, magnetism, and light possible. Gluons are responsible for the strong nuclear force, binding quarks tightly together inside protons and neutrons and giving atomic nuclei their stability. The W and Z bosons carry the weak nuclear force, which drives processes like radioactive decay and the nuclear fusion that powers stars. Among these bosons, the Higgs boson holds a unique role. Confirmed in 2012, it interacts with the Higgs field, which gives mass to other particles. Without this interaction, matter as we know it could not form. Together, these particles and forces fit into a powerful framework known as the Standard Model of particle physics. This model organizes particles into families and describes how they interact to build the universe's structure. It has been tested countless times and has predicted many discoveries with astonishing accuracy. Yet, the Standard Model is not complete. It does not include gravity, the force that shapes planets, stars, and galaxies. It also cannot account for dark matter, the unseen substance believed to make up most of the universe's mass. Scientists continue searching for theories that go beyond the Standard Model, hoping to uncover even deeper layers of reality. Despite its boundaries, the Standard Model provides a stunning glimpse into the universe's hidden order. It shows how the smallest particles, guided by subtle forces, join in quiet harmony to create everything, from your body to distant galaxies. This understanding deepens our appreciation of the quantum world, reminding us that beneath every visible form lies a tapestry of balance, structure, and mystery. woven from the smallest threads of existence. Beneath the particles themselves lies another profound layer of nature's architecture, the fundamental forces. These invisible threads hold the universe together, controlling how matter moves, interacts, and transforms. Scientists have identified four fundamental forces, each with a unique role and range. The electromagnetic force is perhaps the most familiar. It governs how charged particles like protons and electrons attract or repel each other. This force is responsible for electricity, magnetism, and light. It shapes everything from the glow of a candle to the signals in your nervous system. It can act across infinite distances, though its strength fades with separation. Next is the strong nuclear force, incredibly powerful but limited to extremely short ranges. It binds quarks together to form protons and neutrons. It also holds these particles tightly inside atomic nuclei, overcoming the natural repulsion of positively charged protons. Without the strong force, atoms would fly apart, and matter as we know it could not exist. Then there is the weak nuclear force, responsible for subtle yet essential processes such as radioactive decay and the fusion reactions that power stars. Despite its name, this force plays a central role in the life cycles of stars and in the creation of elements necessary for life. Last is gravity, the force of attraction between masses. It shapes the large-scale structure of the cosmos, guiding the motion of planets, stars, and galaxies. Though it is the weakest of the four forces at small scales, its influence stretches infinitely and accumulates over vast distances, sculpting the universe. Together, these four forces form the foundation of physical reality, governing everything from particles dancing inside atoms to galaxies swirling through space. Understanding them is essential to unlocking the secrets of the quantum world and beyond. Among the particles and forces, one discovery stands out for its mysterious and foundational role: the Higgs boson, sometimes called the God particle. While the nickname oversimplifies its nature, the Higgs boson reveals how particles gain mass, the very property that gives them weight and physical presence. The story begins with a question: why do some particles have mass while others, like photons, do not? Physicists propose the existence of a field filling all of space, the Higgs field. As particles move through it, they interact with the field to different degrees. This interaction slows them down and gives them mass, similar to how swimming through thick syrup would slow a person's movement. The Higgs boson is a ripple or excitation in this field, a particle born from the field's energy. It was finally detected in 2012 at the Large Hadron Collider, confirming decades of theory and completing a major missing piece of the Standard Model. Without the Higgs mechanism, particles would remain massless, racing through space at the speed of light. Atoms, molecules, stars, planets, and living beings would never form. The Higgs field's quiet presence makes a solid, structured universe possible. Its discovery marked a turning point in our understanding of the quantum world, reminding us that unseen fields and forces quietly shape everything we experience. Even deeper than the particles we study lies the realm of quantum fields. Modern physics reveals that particles are not tiny solid objects, but ripples or excitations in underlying fields that permeate space. Imagine space as an invisible ocean with waves rising and fading across its boundless surface. Each wave corresponds to a particle, an electron here, a photon there, emerging when its field is disturbed. These fields exist everywhere, even in the emptiest voids of the universe, constantly vibrating and interacting. This view reshapes how we think about matter and energy. Particles are not isolated points, but temporary expressions of deeper fields, always fluctuating and shifting. Sometimes particles even appear momentarily before vanishing again, a phenomenon known as quantum fluctuation. Quantum field theory combines quantum mechanics with special relativity and serves as the foundation for the Standard Model, our most accurate description of particle interactions. It explains how forces are carried by particles like photons and gluons, which themselves are excitations in their respective fields. These fields are interconnected, moving in complex harmony and giving rise to the rich variety of particles and forces that build the universe. Even what we call empty space holds energy, often referred to as vacuum energy, which influences large-scale phenomena like the universe's accelerating expansion. Exploring quantum fields reveals the subtle, dynamic fabric beneath all matter, showing that reality is not made of solid objects, but of a continuous web of energy, interactions, and possibility gently humming beneath everything we know. Even the apparent emptiness of space is never truly empty. In quantum field theory, the vacuum, what we might think of as nothing, is actually a restless sea of invisible activity. Tiny, short-lived disturbances called virtual particles constantly emerge and disappear, flickering in and out of existence in a fraction of a second. These particles are not like ordinary particles. They cannot be directly observed or captured. Instead, they are temporary ripples in quantum fields, allowed to exist briefly because of the uncertainty built into the quantum world. Their fleeting existence is permitted by the Heisenberg uncertainty principle, which allows brief fluctuations in energy and time. These vacuum fluctuations create effects that can be measured in experiments. One famous example is the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a tiny force pulling them inward. This happens because the distribution of virtual particles between the plates differs from that outside, creating a subtle pressure imbalance. Virtual particles also help mediate the forces between real particles. They act as messengers, popping in and out of existence to carry forces such as electromagnetism and the strong nuclear force. When two charged particles attract or repel each other, it's as if they are exchanging a cloud of virtual photons. These photons never live long enough to be directly detected, yet their influence is undeniable. All of this reveals a universe far more dynamic and alive than our everyday senses suggest. The vacuum itself is filled with hidden energy and motion, reminding us that beneath the calm surface of reality is a vibrant quantum dance. This strange, invisible activity forms the foundation of much of the quantum world, deepening the mystery and wonder of existence at the smallest scales. Despite the elegance and success of the Standard Model, it leaves many profound questions unanswered. Physicists see it as a magnificent but incomplete blueprint, like a map of familiar continents that omits entire unseen worlds. One of the greatest mysteries is dark matter, an invisible substance that makes up most of the universe's mass, but cannot be explained by any known particle in the Standard Model. Alongside it is the even more puzzling dark energy, the mysterious influence driving the accelerating expansion of the universe. Neither dark matter nor dark energy fits within current physics, hinting at deeper laws yet to be uncovered. Another challenge is the nature of gravity. Unlike the other fundamental forces, gravity resists being unified with quantum theory. The Standard Model does not include a quantum description of gravity, and attempts to merge it, such as string theory or loop quantum gravity, remain incomplete and speculative. Physicists also wrestle with why the fundamental constants of nature, the masses of particles, the strengths of forces, and other parameters have the precise values they do. Are these numbers fixed and universal, or could they vary in unseen regions of the cosmos or across potential multiverses? Experiments at particle colliders continue searching for clues. The Large Hadron Collider, for example, explores energies that may reveal new particles or forces that extend beyond the Standard Model. These unanswered questions mark the living frontier of physics, where the known meets the unknown. They invite imagination and curiosity as science reaches beyond current limits to uncover what lies deeper in the universe's structure. Among the most astonishing phenomena in quantum physics is quantum tunneling, where particles pass through barriers that classical physics says they shouldn't be able to cross. Imagine a particle approaching a wall it lacks the energy to overcome. Instead of bouncing back, it sometimes appears on the other side, as if it has slipped through solid matter. This defies everyday logic, but is a fundamental aspect of quantum mechanics. At the heart of tunneling is the wave-like nature of particles. Each particle is described by a wave function that doesn't end sharply at a barrier, but rather fades gradually. This creates a small probability that the particle can exist on the far side. Whether tunneling occurs depends on the particle's energy and the barrier's height and thickness. Quantum tunneling is not merely theoretical. It plays essential roles in both nature and technology. In the core of the Sun, tunneling allows hydrogen nuclei to overcome their mutual repulsion and fuse together, releasing the energy that powers stars and warms our planet. In modern technology, tunneling enables tools like the scanning tunneling microscope, which can image surfaces at the atomic scale by detecting tunneling electrons. It also forms the basis of tunnel diodes used in high-speed electronics and is crucial in flash memory, where electrons tunnel through insulating layers to store data. These applications reveal how the mysterious quantum world quietly shapes both the stars above us and the devices in our hands. Quantum tunneling shows that the rules of nature are more surprising and profound than they appear, and that the smallest particles hold the secrets to both cosmic power and advanced technology. One of the most fascinating demonstrations of wave-particle duality is the famous double-slit experiment, which has intrigued physicists for over a century. In this experiment, a beam of light, or even particles like electrons, is directed at a barrier with two extremely narrow, closely spaced slits. A detection screen placed behind the barrier records where the particles or light land. If particles behaved like tiny solid bullets, you would expect to see two bright spots on the screen aligned with the slits. But instead, something entirely different appears. A pattern of alternating bright and dark bands known as an interference pattern. This pattern is a clear sign of wave behavior, formed when waves overlap and interfere, amplifying in some areas and canceling out in others. What makes the experiment truly astonishing is what happens when particles are sent through the slits one at a time. Each particle arrives as a single point on the screen, behaving like a localized particle. Yet as more particles accumulate, the same interference pattern gradually appears, as though each particle somehow traveled through both slits simultaneously and interfered with itself. It behaves not like a tiny ball, but like a wave. However, when detectors are placed to measure which slit each particle passes through, the wave-like behavior disappears. Instead, the particles behave as though they took only one path, and the interference pattern vanishes. This stunning result suggests that the very act of observation changes what is being observed, offering a deep insight into the nature of the quantum world. The double-slit experiment forces us to reconsider basic assumptions about reality. At the quantum level, particles do not have definite positions or paths until they are measured. Instead, they exist as wave functions, mathematical descriptions of probabilities spread through space. When a measurement occurs, the wave function collapses to a single outcome. This experiment shattered classical notions of certainty and locality and remains one of the most elegant illustrations of quantum mechanics. It reminds us that the universe at its smallest scales is far stranger and more mysterious than anything we encounter in everyday life. In the quantum realm, there are also fundamental limits to what we can know about certain properties at the same time. This is captured in Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. It states that the more precisely we try to measure a particle's position, the less precisely we can know its momentum, and vice versa. This isn't due to limitations in our instruments, but a fundamental property of nature itself. Imagine trying to pinpoint exactly where an electron is. The act of measuring its precise position inevitably disturbs its momentum, making it impossible to determine both with perfect accuracy at the same time. This isn't just a technical issue. It reflects the built-in fuzziness of particles at microscopic scales. The principal challenges classical thinking, where objects are assumed to have definite, predictable positions and velocities. Instead, at the quantum level, particles embody probability and uncertainty, resisting precise description. Heisenberg's principle has deep implications. It means the universe has an inherent limit to predictability, placing a boundary on the exactness of measurement and knowledge. This uncertainty isn't only theoretical.